Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. Salam sejahtera. Okay, my name is Zainul. I'm from the School of Chemical and Energy Engineering, Faculty of Engineering, University of Malaysia. And today we are back again under this distinguished lecture series. And today we are very fortunate and grateful to be having our next speaker all the way from Hawaii. Yeah, I think this is the furthest that we have a speaker to date. He with a time difference of almost 18 hours. Yeah, he's now like 3 p.m. over there yesterday, and now we are at 9 in the morning today. Yeah, so we have Professor Samir Khanal today. So just a little bit about him, how we get to know each other. We attended some conferences under the auspices of Biotechnology Research Society Institute of India, BRSI. So we are both under the category of international speakers. So that's where we get to know each other, and most of the time we'll discuss, and during the coffee time we discuss about what we can do together. And so hopefully after in the near future we can see some collaborations between UTM and University of Professor Samir Khanal's University. Yeah, so I know everybody like is not can't wait to hear Professor Samir Khanal's talk today. So with that, I would like to pass the session to Professor Rafiq, our distinguished dean, to introduce our speaker today. Please, Prof. Thank you very much.
Thank you very much, Zainul. Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone to our 64th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome our distinguished speaker all the way from the Pacific, Professor Samir Kumar Khanal from University of Hawaii at Mānoa, Hawaii. A bit about our distinguished speaker today. Dr. Samir Kumar Khanal is Professor of Environmental Engineering in the Department of Molecular Biosciences and Bioengineering, University of Hawaii at Mānoa. He obtained a Ph.D. in Civil Engineering with a focus in Environmental Biotechnology from the Hong Kong University of Science and Technology in 2002. Masters of Science in Environmental Engineering from the Asian Institute of Technology, Bangkok in 1997, and Bachelor of Science Honours in Civil Engineering from Malaviya National Institute of Technology, Jaipur, India in 1993. Dr. Khanal was postdoctoral research associate and research assistant professor in the Department of Civil, Construction and Environmental Engineering Department at Iowa State University. His research focuses on anaerobic digestion, waste to resources, aquaponics, nanobubbles technology, and removal of pharmaceutical compounds. He has published more than 110 papers in high-quality international journals and edited 10 books. He also wrote a book on anaerobic biotechnology for bioenergy production, principles and applications, produced by Wiley-Blackwell, which became the bestseller. He also wrote a bioenergy textbook, Bioenergy Principles and Applications. Dr. Khanal is an associate editor of Bioresource Technology and was the recipient of Board of Regent Medal for Excellence in Research in 2018 and CTAHR Dean's Award for Excellence in Research in 2016. Dr. Khanal is a professional engineer in the state of Iowa. So that is a brief biography of our distinguished speaker today. Here now is Professor Samir Kumar Khanal from University of Hawaii at Mānoa, Hawaii, with his talk on waste to resources in the context of circular economy. Professor Samir Kumar Khanal, over to you.
Thank you so much, Professor Rafiq, and also Janul. I'm going to share my screen with you all. So very good morning there. It's good afternoon here. So today I'm going to give you a look in the field of waste to resources and how it relates to the circular economy context. And if you want to see more details, you can actually see from this my website. Let me see. So let's see, double screen is coming. Let's see. Anyway, so I'm going to start now. Before we begin, I just wanted to give you a little bit about the whole context. And one of the major important part is actually the population growth. So there is actually a very nice video which was developed by the American Museum of Natural History. And if you want to see this one, this actually tells you human population through time. I may try to show you part of this video so that you understand how the population growth actually took place. Let's see. Doesn't play. What's going on? So unfortunately, something is wrong. It didn't play. But anyway, so I just wanted to give you a perspective that the human modern population evolved somewhere 200,000 years ago, and about 100,000 years ago, population started to move worldwide. And then, if you look at the population growth, until before 1 AD, we had only less than 1 million population. By the start of 1 AD, the population becomes somewhere about 170 or 180 million. And it was only in the 18th or 19th century when there was industrialization and development of modern technology, population started to grow very rapidly. And now we have about 7.7 billion population in 2018. And now in 2050, the population is going to be about 9.5 billion. And by 2100, we expect the population will reach somewhere about 11 billion. So there is a significant pressure because of the growth in population. So now this whole comes into the perspective of the grand challenge 2050. What is the implications of those growing population? One of the major issues, certainly, we have to supply enough clean energy for this growing population, which is renewable. That's one major issue. A second important issue would be food safety and food security. Providing enough food for the growing population could be another issue. At the same time, we will also have another big challenge, which is environment, including providing clean, potable water for a growing population, including waste management, and then also climate change because of emission of greenhouse gases. And last but not the least, we are also facing uncertainty. And this uncertainty also came in recent times, such as diseases, the extreme weather pattern, which is showing in many parts of the world. So these are some of the grand challenges that we have to face in recent times. And if you look at the carbon dioxide concentration in the atmosphere, it is very clear that before 1960s and 70s, our greenhouse gas, especially carbon dioxide concentration, was less than 320 ppm. But now in 2014, the population crosses the CO2 concentration in the atmosphere crossed 400 ppm, and now it's about 420 ppm. So there's a significant increase in the CO2 concentration in the atmosphere. And this increase in CO2 concentration is essentially a factor for the climate change or extreme climatic conditions. And if you look at the total CO2 emission because of the global energy-related use, it is about 33 gigaton. And then this implication essentially is going to be, the flooding of coastal areas and melting of the glacier ice. So these are some of the implications because of the population growth and use of the fossil-based energy. And if you look at the some of the effect of COVID-19 lockdown, which we saw recent times, There was some positive effect on the environment. We saw a sudden drop in the CO2 emission because of less use of carbon-based fuel or fossil-based fuel. So we can see there was a significant drop in the CO2 emission. And at the same time, this is on the year basis. Also on the month basis, we saw a significant drop in the CO2 emission because of the less use of the fossil-based fuel. In the US, we also saw a significant drop in the CO2 emission, especially because of the lockdown. And in April, the CO2 emission was only about 307 million metric ton, which is much lower than 400. So there is some positive side of the lockdown. And also in global scale, there was 60% reduction in the air pollution in major cities in the three weeks lockdown period compared to last year. So these are some of the positive side, I would say, because of lockdown, where we saw some changes in the global environment. Now our current model, the global model, is essentially what called linear model. That means we are essentially taking all the resources from the earth and we make product and then we just use them and we throw them or waste them. So these are essentially linear model of our society to sustain the quality of life. So we are freely drawing all the raw materials from the earth, from different resources, because they are they will consider they are abundant, but they are not. And at the same time, we produce significant amount of solid, liquid, and gaseous waste pollutant. And in the absolute and also per capita basis, US is probably the country that is the highest consumption of all the resources. And there was a report, very nice report that came out, water waste too. And this essentially gives you the quantity, some data on the waste management side, solid waste side. So if you look at this data, we generate about 2 billion, slightly over 2 billion metric tons of the solid waste in, I think it's about 2018, around that time. And then about 2050, there will be a 70% increase in the solid waste generation, which will be about 3.4 billion tons. So a significant increase in the solid waste generation you are expecting. And most of those waste are coming from many of the Asian countries. If you look at this one, there's countries in Asia, East Asia, Central Asia, and South Asia. So these are the countries where you can see a significant increase in the generation of the waste. Now, if you look at the solid waste management practices, we have a hierarchy. The first one essentially is not to produce waste at all. So reduce in the use of material is one factor to reduce the waste generation. So reduce is one factor. Second one is reuse. That means using anything by many people. So reuse could be second strategy. Third one is what we call recycling of the waste material or composting. And then the next step is essentially energy generation by waste to energy. And last part, which is less favorable, is landfill. So that is the hierarchy of waste management. So to implement a zero waste management practices, what we call reduce, reuse, recycle, and compost, 3RC concept. And then followed by the waste to energy, which means converting waste into energy through either thermochemical or by the biological process. And landfill is the least preferred options of waste management. Now, there was a very nice report that came out in the National Geographic magazine, and which called "Is the World Without Trash Possible?" And if you look at this particular chart, you will say that we actually use somewhere about 93 billion metric ton of the raw material resources. It could be renewable resources, it could be non-renewable resources. So these are the total amount of resources we use to run our bioeconomy, our economy. And if you look at some recycle reuse, which would be about maybe 9.2, so altogether about 102.9 billion metric ton of the resources are being used annually to fulfill our needs, our daily activity. And out of that, you will see that 2/3 of the material are being disposed, emitted as a different source of pollutants, either in a solid form, a liquid form, a gaseous form. So about 68% of those are essentially become waste. So very small amount are being reused or recycled. So if you look at recycling back, it's only about 9.3 billion metric ton, which is a very small amount of this material. And that's mainly from the biomass material. So very less amount are being recycle or reuse. So if you look at the circular economy context, which means the material are being reused within the system. So this is also one of the very nice diagram come out from the National magazine, National Geography magazine. If you look at, there are two factors. One is called biological nutrient and one is called technology nutrient. So if you look at this particular slide, you will see we have renewable resources, we may have renewable energy, and then we have finite resources which are non-renewable. They are all going into the system. We get a material, we produce product and services, and finally they are used by consumer, and then the final product is essentially waste. But in this circular economic context, we have different technological nutrient and then biological nutrients. So if you look at this one, the technology nutrient side, we have a recycle. That means you are converting this metal into some basic nutrient element by recycling. And you can also have a refurbish. That means you are essentially making a new product, like a new product from those material. You also have reuse. That means the product is being used by a large number of people for a long time. And last one is essentially repair. So you are repairing the product so it has a long lasting time. So these are essentially we call technology nutrient. At the same time, we also have a biological nutrient side where you will recycle this material in the form of nutrient for different activities. So it includes composting and other type of biological conversion processes such as anaerobic digestion, where you are reusing those material for producing different type of products. So these essentially two type of concept I applied, and by this way we are reducing the amount of waste that is being disposed. And one very simple strategy of circular economy is how you design a product. So if you look at this simple kettle, this kettle essentially consists of very different components. It has it has a filament, handle, pot, different part. So in the modular design, what they do, they essentially have a product that are essentially designed and developed in such a way that each component can be separated easily. And if some product doesn't work or they are broken, you can replace that individual product without disposing whole component. So that essentially gives you a component of reducing the amount of waste that you produce. So these are essentially modular design. And many of the computers are also now modular design. So you don't have to throw the computer. If your monitor is not working, you can replace your monitor. If your hard disk is not working, you can replace only your hard disk. You don't have to dispose your computer. So these are modular design that will reduce the amount of waste you produce. So that is essentially one of the strategy of reducing the waste in the circular economy. And also you may also wonder quite often that we have different planes coming up. In recent years, there was a Boeing 787 Dreamliner, and this is essentially a much better version than the bigger Airbus 380 or Boeing 747. Now they don't actually produce these big planes like 380 and 747 because there are many drawbacks. And this new Boeing 787, they are very fuel efficient. It reduces the fuel consumption by almost 20%, which is very efficient. They are lightweight because they are made of composite materials. So they use less amount of material. And then also at the same time, it has a smaller plane and a smaller airport size. One problem with the composite material comes is that when you have composite material, it becomes a little bit difficult to recycle, because recycling of a material depends on the purity of the compound. If you have a diverse compound in any material, in any product, then recycling becomes much difficult. So in a composite, you have 2 or 3 or 4 different materials. So it's very difficult to separate each component, and that makes it a little bit difficult when it comes to composite material. If you have only 1 or 2 material in any product, that's easy to recycle. So that's one of the problem. Otherwise, they have a lot of other positive sides. So that is essentially what we call design for environment. And if you wanted to listen, much good discussion about circular economy, there was a TED program, a TED presentation by Cillian Lujan. So you can actually watch this one. They have 6 or 7 minutes. Because of time, I'm not going to go to this video, but I have the link there, which you can actually see it and then get some idea about circular economy. With this one, I'm going to go and talk about some of my work in the context of circular economy. So I have been working on the anaerobic digestion for quite some time. You may wonder what really anaerobic digestion is all about. So anaerobic digestion is essentially a biological processes which are carried out by the bacteria in absence of oxygen, and it converted different type of waste materials, especially organic waste material, into methane and carbon dioxide. And this process occurs in many natural systems such as ocean, lakes, sediment, a paddy field, marshland, even the digestive tract of a human being and an animal. So these are a very common processes taking place in the nature. So we essentially get those information, those ideas, and then we use this idea for developing the AD technology. So in this particular process, if you look at this one, we have a digester, what you call anaerobic digester. So we feed this digester with different type of waste material. It could be manure coming from different type of animals. Also, it contains different type of industrial wastewater that has a high organic content. You can also come with domestic wastewater, food waste, or different type of biomass material, agri residues. So you feed them into this digester. Stay there maybe about 30 days or 40 days. There's a bacteria, that oxygen, they break down this organic matter and it produces biogas. And this biogas consists of methane and CO2, which is one of the product of the anaerobic digestion. And then we clean them. Sometimes it has some hydrogen sulfide, so we can remove hydrogen sulfide. It is saturated with water, so we can also condensate, remove all the water. And then the biogas we produce, we can directly burn it. In many places, they burn it, used for cooking purposes, lighting purposes. Sometimes they also use for heating and cooling and cooling purposes as well. So this is direct burning of the gas, very commonly used in many developing countries where they don't have any firewoods or other cooking, energy. So they use this for cooking. You can actually upgrade the biogas. So you can remove all the CO2 and make the biogas rich in methane, which about maybe 98 or 99%. And once you upgrade the biogas, that become like a natural gas, you can pressurize them, you can inject into natural gas grid, or you can actually use this one as an LPG for car and transportation applications. So that's one of the applications of the biogas. Or you can burn the biogas into a cogeneration unit called combined heat and power, and that essentially produces electrical energy and thermal energy or heat energy. The heat energy is used for heating home, especially in the winter time in the northern part of the hemisphere. And this electrical energy are then transferred into the grid and then supply the energy. That is the gas part. The solid part, which remains of the after digestion, is called digestate. It contains both liquid and solid. You store them for some time because it has some methane. You capture this methane. And then you can separate them liquid and solid by either centrifuge or just other means of separation. And then liquid can be applied in the field as a fertile irrigation. It has a lot of nutrient and water, so you can use this for agricultural application, for growing plants, for edible plants. And then solid part, you can either apply to the land as a biofertilizer, or you can compost them with other raw material and make a compost and apply to the land. And at the same time, you can also directly transport the whole solid and liquid part and apply it to the agriculture or gardening. So this essentially gives you a concept of like a biorefinery. Nothing is wasted. Everything is being used, producing energy and producing a valuable biofertilizer. So they're converting waste by the anaerobic processes. Now, question comes, why anaerobic digestion? Because anaerobic digestion produces clean energy, renewable energy from different type of waste material that can be used to produce stationary power or can be used to produce transportation fuel. And also anaerobic digestion can handle different type of waste material, including animal manure, food waste, different type of bio waste, and at the same time, it can also handle sewage as well. The technology is quite mature. There are thousands of plants currently in operation in many countries. And also it can be developed in a remote area where there is no electrical grid. And also it has a potential to reduce greenhouse gas emission because you are essentially preventing the waste being digested and converting into methane in the landfill. So they are being captured. At the same time, it also replaces your fossil fuel. So it reduces greenhouse gas emission. And there's also one technology for waste remediation. So these are some of the benefits of anaerobic digestion. We can also look at beyond biogas. Biogas is a very low value product. We can actually use waste for anaerobic digestion for food production. So sometimes we can digest material, produce nutrient, and apply those nutrients in the agricultural field for food production. This is also one area. We can apply biorefinery concept, producing multiple products. We can also convert sometimes some of the material into high-value biochemicals, volatile fatty acids. Even we can produce methanol from biogas, so different biochemical can be produced. And sometimes digested is very valuable than the biogas. And also biogas can be used for transportation fuel, which is LPG or CNG type of fuel. And there's also technology for wastewater treatment and waste remediation. So these are some of the important applications beyond biogas in the anaerobic digestion processes. So I'm going to give you one very typical example in Cambodia, where they use very small scale digester. This is a very small scale digester. The capacity could be 1 to 3 cubic meter, where they supply their waste material coming from different animal manure or some food waste. They put in a digester here, stay there maybe 20, 30 days. They produce biogas. That biogas is used for cooking. And the digested part, which is here black material, it is very rich in nutrient. So they use this one to apply to the agricultural field, especially in the rice farming, paddy farming, where they supply this as a source of nitrogen, phosphorus, and potassium, other nutrients, so they can grow in growing their rice. And at the same time, they also use digested for producing fruits and vegetables, horticulture application, which is you can see here, they can grow different type of, you can see here, there's a bitter melon here, and then also different type of herbs that are grown on this digested material, which are very rich in nutrient, and they are considered to be organic product, and you can sell in the market in a very high price. They also use digested slurry from this digester for aquaculture application. They feed this one into fish tank, fish pond, where they grow algae, and the algae become the feed for the fish, so they also use for aquaculture. So essentially, digester become really a good source for them to supply rice, supply fruits and vegetables, and also supply protein in the form of fish. So this essentially provides a very niche, life or social uplifting in a rural area. So this is on application of the anaerobic digestion processes. Now, anaerobic digestion can handle a very different type of waste material. Some of the waste material are very complex, such as biomass. We call lignocellulosic biomass. And they are one of the most abundant resources on the earth. We can produce about 200 billion dry ton per year from this material. And they are abundant in our earth system. So we can use this one also in the anaerobic digestion. One of the problem comes when it comes to biomass is because they are very light. The density is less than water. So when you put in the digester, they started to float on the surface. They essentially become a forming problem in the digester. They're also very rich in carbon, but less nutrients, so there may be nutrient deficiency. Of course, they are very recalcitrant, very difficult to degrade by the bacteria because they are composed of cellulose, and then lignins, which are very difficult for the bacteria to degrade it, so they are recalcitrant. So we did some studies on this one. So if you look at the vertical reactor like this one, when you run this biomass into reactor, after some time, the biomass started to float on the surface, comes on the top, and then clog everything. So they become quite dangerous because once they clog, the reactor becomes pressurized and it may just blast out. So that is a problem when you have the vertical reactor. So we developed horizontal reactor, as you see here. In the horizontal reactor, what happened that there's a pedal, that pedal moves continuously, and that helps to break down any formation of scum. So you don't see any scum formation, and that is essentially quite safe for operating a biomass that is very light. So that essentially becomes a very, very simple operation when you look at the biomass digestion horizontal reactor. It doesn't form much scum and so forth. So we developed this kind of reactor. And in this kind of system, what happened that when you digest biomass, mostly it is the hemicellulose component, which are amorphous structure. So therefore, they are the one mostly digested by the bacteria. They are degraded by the bacteria, which is about 7 to 22%. So they are mainly converted into methane gas. But cellulose and lignin will remain in the solid phase. So they are not quite degraded as the hemicellulose part. So you have the digested material, the solid material, which are very rich in cellulose and lignin remain there. So you are only converting maybe 20% or 30% of the biomass into biogas. So what shall we do with the solid? Then we came with the idea of anaerobic digestion biorefinery. So when you have this kind of biomass material, we essentially convert part of the biomass into biogas by anaerobic digestion. The solid part, we can essentially separate solid and liquid part. And the solid part, which is very rich in lignin and cellulose, that can be hydrothermically be converted into, uh, hydrothermal hydrochar or biochar, or it can be torrefied, producing torrefied biomass. And this torrefied biomass is now very rich in the energy because of high lignin and cellulose. So you can actually use this one for co-firing the coal-based bioplant. So you can actually use for producing electricity in your coal-based power plant because that has a very high energy content. You can also convert this biomass into nanocellulose, a biopolymer, bioplastic, and also you can produce membrane. So these are some of the applications of the digested material that comes out after anaerobic digestion. So you can essentially produce a multiple product from the biomass using the anaerobic digestion biorefinery. Sometimes what happens that you have a substrate which are very different. They have a different nutrient composition, and some are very easy to digest, some are very difficult to digest, some has a high carbon, some has a low carbon, some are rich in nutrients, some are poor in nutrients. So in that case, we do what we call the co-digestion technologies. In co-digestion, you digest 2 or 3 substrate, you mix together, so it balances a lot of limitation of the single substrate. So in a co-digestion, if you look at this one, it provides a synergistic effect. That means it improves the digestibility. So at the same time, you can also produce the digested, which are very rich in nutrients. So that can be good for agriculture application. It provides better process stability in the anaerobic digestion processes. Sometimes it contains some toxic compound. By co-digestion, you can reduce the toxic compound by dilution. And also sometimes some of the waste can generate ARG or ARB. But in anaerobic digestion, it reduces what we call the antibiotic resistant gene or active antibiotic resistant bacteria by anaerobic digestion. So it produces the digested which are less in ARG and ARB. So these are some of the benefits of co-digestion. Sometimes we do co-digestion of food waste with the sewage sludge. Food waste sometimes has much higher nutrient content, and also it has an easy digestible compound, but sludge is not very easy to digest, so we can mix together those compounds. Sometimes we can do co-digestion of agri residues, animal manure. Agri residues has a very high carbon. Animal manure has high in nitrogen, so they balance out the nutrient and provides a good balance for anaerobic digestion. So these are some of the benefits of co-digestion. I'm not going to go in detail because all can be found in my publications. I'm just going to leave here this one. In recent years, we have been working on what we call the micro-aeration. So what happened that in the anaerobic digestion processes, when you feed the waste material into the anaerobic digester at a high loading rate, it produces a lot of VFA, volatile fatty acid. And these volatile fatty acid are organic acid, such as acetic, propanedic, butyric acid. The high concentration of VFA will essentially lower the pH, and at the same time, it will inhibit the methanogenic processes. So we develop a technology where we actually can supply a small amount of oxygen into the reactor, a very small amount, by controlling the oxidation reduction potential. And by supplying a small amount of oxygen, we can selectively reduce BFA concentration to the level that methanogen bacteria will not be inhibited. And we can continue to produce biogas by micro-aeration. So we developed micro-aeration technology for treating a waste material at high concentration, high organic loading rate. And we found very interesting findings in our study. So when you have complex materials such as biomass, the first step is actually hydrolyzing bacteria. So you essentially hydrolyze this complex into a soluble form. You put a soluble sugar by the hydrolyzing bacteria, and then at the same time you have estrogenic bacteria that convert this soluble sugar into volatile fatty acid and producing some hydrogen. Now, if you inject a small amount of oxygen, what happens that the part of volatile fatty acid are essentially being consumed by the facultative bacteria, converting some of this organic matter into CO2 gas, and then at the same time, it will also consume oxygen. And then what happened that the acidogenic bacteria will convert some of those volatile fatty acid to acetic acid. At the same time, some of the oxygen will be consumed, converting acetate into CO2 by the facultative bacteria. So you have CO2 that are formed here, and excess hydrogen formed in the process will combine and forming a methane by hydrogen-tropic methanogenesis. At the same time, it reduces the amount of acetate built up in the system. So by this way, you can somehow bypass or reduce the buildup of acetic acid. At the same time, you continue to produce methane by hydrogen-tropic methanogenesis. So this is the new pathway we found when we have complex substrate and we have micro-aeration. So these are essentially one of the very interesting study we did on the micro-aerobic processes. Details can be found in this publication. I'm not going to go in detail in interest of time, so I'm just showing some of the references. Now, the next step is looking at the food waste. Food waste is a major problem globally. If you look at the global production, we produce about 1.3 billion tons of food waste every year. About 1/3 of the food we actually produce are essentially being wasted. So economic loss is about $750 billion annually, significant amount. And environment impact is significant. The carbon footprint is about equivalent to 3.3 gigaton of CO2 equivalent produced because of the disposal of the food waste in the landfill. And this is the third largest greenhouse gas emitter after US and China. So see, there is significant environmental burden of the food waste. So we try to find out if there is a different way that we can convert this food waste into high value product. One way of doing is actually growing or cultivating some insect. There are some insect called Hermesia illucens. These are called black soldier fly. These insects are essentially very common in the tropic and subtropic areas. They colonize onto organic waste, and they also reduces the odor formation, pathogen, and other type of arthropods. So these are a very benign type of insect that can consume the food waste, and they doesn't produce any type of disease, and they don't have any mouth, so they don't consume any food. The insect will not consume any food, and they are only the food consumer is their larva. So when they produce egg, the egg will convert larva, and this larva will turn into the pupa, and these are the ones they actually consume the food waste, and they are the voracious consumer of the food waste. And about, if you look at 25 to 50 milligram of organic matter are consumed per larva per day, so significant. The life cycle is about maybe 40 to 50 days time. So that means once the egg is laid down, it will take about 41 days to become insect. When they become insect, they lay egg and they die. So that's essentially what their life cycle is all about. See if it's not conjugate. So there's no any, there's no. So from this one, we can see that there's a significant opportunity for insect farming from this one. As you see here, that there is a different type of waste material. It includes a lot of food material, including a lot of this produce, what you call produce, the leafy vegetables, fruits, everything. So this insect will essentially lay eggs on the waste material, and they produce this larva. And this larva essentially become pupa, and this contain about maybe 25 to 30% is fat, and the remaining part, about 30-35% is actually the protein. So you can essentially extract the oil from this insect that become converted into biodiesel, and the meal that comes out from insect actually are very rich in protein, maybe 60-70%, and that can be used as an animal feed application. So this is essentially the insect, as you see, growing the waste material, and these essentially are the larvae stage, and that essentially can be used for converting food waste into animal feed. And These are some of the publications in converting these food waste into the animal feed by the insect farmers. Now we also work on what we call mycological processes. In mycology, we use some fungi. These fungi are edible fungus. This fungus can convert wastewater into fungal protein, very rich in protein, maybe 50% protein, and that can be used for animal feed application. Some of these fungi are also very good in degrading petroleum and polyaromatic hydrocarbon because they can produce enzyme peroxidases and they can break down the hydrogen and carbon bond and they can degrade those pollutants as well. So these are very important fungi, and they can convert this waste into protein, but at the same time degrade the very this waste material. So here we are looking at fungal protein production. If we say fungi, mushroom are also fungi, but these are the microfungi. This means they are very small size here. And they can grow in a different type of waste material, including the raw wastewater coming from sugar cane to ethanol plant, molasses, here food processing wastewater, soya waste, brewery waste, you name it. All the wastewater coming from food processing industries are very rich in organic matter, and they can be good source for growing those fungi. And these fungi are edible fungus, and they don't produce any type of metabolites. They are toxin, and they are actually isolated from tempe, which is a very common Indonesian delicacy. And then we can put those fungi into the reactor like this, and we supply wastewater, we supply air, and they will grow on this waste material and then produce fungal biomass. And this fungal biomass can be separated and become fungal protein, and that can be used as the aquatic feed or animal feed. And if you look at this one, these are essentially the fungal species are growing into the bioreactor, and they actually form a very circular pellets structure. The pellet diameter could be somewhere maybe 2 to 3 millimeter or 4 millimeter size. So quite big pellets they are formed. This is a cultivation time, 16 hours, they form pretty big. 24 hours, they become almost full of the reactor, and 48 hours is too long. This essentially becomes more like anaerobic. So within 1.5 days or less than 2 days, you can actually convert waste into protein-rich material. And the air supply is somewhere between 1.5 ppm. That means 1.5 volume of air per volume of reactor per minute. That's a flow rate. And then very interesting thing is that if you look at a different type of bioreactor, we have airlift reactor and bubble column reactor, two different type of reactor. And then if you look at the bubble column reactor, means you're just injecting the air from the bottom side. You can convert 1 gram inoculum into 8 gram of the fungal biomass. So that means you're adding 1 gram biomass, you can get up to 8 to 10 gram biomass. Significant amount of biomass, which is much more than chicken and other type of animal products. So your yield is much higher from those fungi. And then these fungi are very rich in different type of nutrient. Protein, crude protein is almost 50%, which is very similar to soybean meal. Lipid content is also about 6%, which is so slightly less than a fish meal, but it is a less ash content, less than 4% compared to fish meal. So this is a very good source of protein for human being and also for different type of animal food applications. So this is also a source of converting waste into protein for animal feed and human feed application. And also digestibility is pretty good. 84% can be digested by the in vitro testing. So that is essentially a good indication that it has a good source of animal feed application. And these are some of the publications in the field of converting waste into fungal protein. In recent years, we have been working on the nitrogen pollution control. So we actually look at how can we recover nitrogen from different waste materials. In the agricultural production system, we use a lot of water and we use a lot of inorganic fertilizer. And once you apply fertilizer, because we have to supply fertilizer to grow plants, to grow food, more than 90% of the input are actually waste. They goes into water bodies, become water pollution, and also it emits nitrous oxide, that is become global warming. At the same time, this nitrogen pollution will come algal bloom, eutrophication, and all has implications on human health. So essentially, there's a lot of implications of nitrogen pollution in our environment. So we are looking at the possibility of what called aquaponics, so where we can capture some of the nutrient, excess nutrient from those processes and grow plants, and that this plant can be used as a food application. So that essentially is one of the projects that we have been working on aquaponics. So aquaponic is essentially a processes which is a soil-less system that we don't use any soil. So we have essentially the tank that contain essentially the what we call the some plastic support media here or some styrofoam. We have the bucket type system where you plant your different plants. You allow the water from aquaculture system to come here. Essentially, the water first goes into biofilter where they convert this ammonia into nitrate, and this nitrate are now become nutrient for those plant. They take up this nutrient, they grow, and then at the same time we clean the water, we recycle water back into the tank. So this is essentially a zero waste system and process to recover the nutrient in the form of edible plants. So this is called aquaponics. And this is essentially the processes, how it occurs. This is the biochemical processes where we provide fish feed for the fish, and the fish will consume some of the fish feed for the body mass. About maybe 70-80% are converted into waste, and that become ammonium. Then there's a bacteria called ammonia oxidizer converted into nitrate, and the nitrate would essentially become nutrient, and that nutrient are essentially taken up by the plant and they grow vegetable, and some of those are essentially being converted into waste material. Some there's some loss in the form of denitrification because there's not enough oxygen. So essentially the process will convert ammonia into nitrate, and nitrate are taken up by the plant, and we convert this nitrate waste into plant biomass for food application. So this is called aquaponics. So we can grow tomatoes aquaponically without soil. We can grow pak choy, we can grow saib, you name it. So you can grow any type of plant that you can grow on the soil that can also be grown in the aquaponic system. And most important part is like the root system. So root system essentially capture the nutrient from this water and convert them into biomass. So depending on how dense the root is, the more effective the plant is in capturing the nitrate. If you look at the tomato has much higher root surface area. So it essentially captures more of the nutrient compared to saib, which has a less amount. Pak choy and lettuce also are very effective in capturing the nutrient from the waste material. So this is actually one of the areas that we have been working. Many publications, I'm not going to go in detail in interest of time, but this also area of recovery of the waste in the form of food. Now, in recent years, there has been also a lot of work on the biochar. So biochar are essentially a product that comes out from the biomass when you do a pyrolysis, which is the heating the biomass in low oxygen concentration at low temperature, somewhere maybe 500 to 700 degrees centigrade. When you burn the biomass, it converted into char called biochar. And this biochar has a very different functional group on the surface, very porous structure. Because of this property of the biochar, it has many different applications. It essentially provides surface for capturing different type of nutrient. In our study, we actually use this biochar to recover sulfide from the biogas. So essentially capture sulfide efficiency was over 98-99% of the sulfide was removed from biogas. So biogas was sulfide free. And once you get the sulfide in the biochar, you can actually apply this biochar as a source of micronutrient, because sulfur is also very important nutrient for plant growth. So you can capture the sulfide in the biochar and apply the biochar in the land. And at the same time, you can also use biochar for removing different type of contaminant from your wastewater as well. Different type of dye, different type of antibiotic, different type of metals, so forth. So this has a lot of environmental applications. Some of the publications in the field are given here. I'm not going to go in detail. In recent years, we have been working on the nanobubble technology. So people talk about what is nanobubble. So nanobubble are essentially bubble which are very small in size. Their diameter could be less than 1,000 micrometer, or in 1 micrometer or 1,000 nanometer. So they're very small size bubble. Because of the small size nanobubble, it has many different properties. It is very easy to dissolve in the liquid phase. It stays in the liquid phase for a very long time. It has a negative zeta potential. They are very stable. So it has a lot of different applications. So we are using nanobubble technology for many different applications in environment and agriculture. There's a machine that generates nanobubble, and the nanobubble can be used for removing different contaminant, for aerobic fermentation, for fungal growth, for also growing algae biomass, and so forth. So it has many different applications. One of the important applications is it also produces reactive oxygen species during the process of nanobubble generation. And these reactive oxygen species are actually very good for disinfecting any of the microbial groups. So they can kill the microbial community or pathogens, and therefore you can reduce the use of chemical-based, disinfectant. So this is essentially a way of cleaning the water using nanobubble and not using any type of chemical. So these are new technology that we are working on in agriculture and environmental application. And these are some of the books that we develop in the related field. And I think that's pretty much what I have so far. And thank you for listening. And I'll be happy to take any question you have.
Hi, Samir. Thank you very much for the very informative presentations. We got a lot of comments at the our Facebook saying that they learned so much from your presentation. Yeah. Okay, Samir.
Yeah.
If I may, if I may ask for you to close your PowerPoint presentation.
Sure, I'm going to stop.
Yeah. So that you can read the question posted on the screen now. Can you?
Yes.
Can you
Yes.
Okay, this is actually from one of my best friends.
I see.
He is also the director for UTM Sustainability.
Mm-hmm.
So his question is, circular economy in waste management is well known in their fundamental studies. Do we have serious practical solution in converting the value of biogas into small footprint for urban isolated area? Yeah, this is very significant because we have a lot of approaches available around using different types of anaerobic digester. So I think his main question is this feasible to be done in an isolated area in terms of its sustainability?
This is a very good question, actually. In many cases, in the biogas sector, the biogas itself is not really high value product, and in many cases, because biogas is very low value product, they don't generate much economic return just by producing biogas. So therefore, in many European countries, they don't actually sustain economically because they don't get much benefit from the energy sector itself. So major benefit comes from a couple of things. It comes from either getting some incentive from the government in terms of waste management side. So major benefit is coming from the waste management side. If you look at the waste side, the disposal cost of the waste is somewhere maybe, I don't know in Malaysia, but in some countries it costs about $100 to $120 per metric ton for tipping fee. So a significant amount of resources or the revenue is coming from tipping fee generation from waste. So therefore, one area is looking at collecting tipping fee from this waste material. And the second part, in my opinion, is actually looking at the digested application. So if we can convert digested into high value product, it could be compost, could be one possibility, which we are looking at. The compost can be mixed and convert and selling as organic fertilizer. So in the urban setting, there's a problem because you have too much waste and you don't have land to dispose of the waste. So that become a challenge, especially when you want to look at the urban setting. So this is one challenge. So therefore, urban setting, what we do, we convert this one into anaerobic digester, and we try to reduce the size of the sludge we produce, especially. So therefore, urban setting, there is a significant challenge because of the area. We don't have enough area for the disposal of the waste material, digested material. So in that case, what we can do, you can sometimes pelletize the waste material. You can form in the pellet form by generating the biogas you produce, and you form like a dry solid material, and you can ship it like a fertilizer in the rural area. That could be one possibility. So once you make it your total solid content less than 10%, the moisture content less than 10%, it's very stable, and you can apply to the land, faraway land, especially those waste material. But there are a couple of things comes. We have to look at it doesn't contain any toxic compound, heavy metals, other type of things are not disposed. They are strictly prohibited. It only contains food waste. And if we are doing co-digestion, sometimes they do co-digestion. That means we digest sewage sludge with the food waste. Then we want to make sure that it doesn't contain heavy metals in large quantity and also no pathogens. Those are need to be taken care of. But I think if we have a biogas, we can use the heating value, the biogas for heating purposes, drying out into solid form, and then shipping this a little far away. So that essentially becomes one of the model for looking at the urban isolated area disposal. So if we can actually combine this one with the organic farming, could be one possibility. If we have a large area, you can actually do organic farming by using waste material coming from those industry and monitoring the environmental quality of the compost or the digested and producing the organic product. So that model may work out, but certainly you get benefit of you must collect tipping fee to meet your expenses. That's important part.
Yeah. Okay, bro. Thank you very much for that. We have another question by Professor Fadil. That one, the previous question was about anaerobic digestion from rural area, right? How about this question in wet market? Do we have smart solution for wet market? Because from the wet market, you have a mixture of waste. We have parts of oily matters, stress, and as well as other organic materials. So maybe if you have any experience in this, maybe you can share some examples.
There are a couple of small plants. These are called they essentially what they collect the recycled oil or fat material, greasy material, and they separate them. How they do it, these plants are very small. They are only 1 million gallon per year plant. So they're very small plant. So what they do, they collect all those fatty or greasy material. It goes into a distillation column or a column that heats them. By heating them, they essentially separate those oily material with the solid material. And the oil part they separate and they convert into biodiesel, and those biodiesel are essentially used for locally industry. Again, they get benefit of what called renewable fuel standard incentive from the government and also in municipality, and also they collect the tipping fee from those restaurants where they have those waste material, and the solid material what they produce they essentially go for a digester part. So that is one possibility. And some of the digester, they can also be run if you have a small amount of oil or grease, you can mix together, you can digest it as well. And there can also be possibility, but if you have too much oil, that become issue because it essentially forms a scum layer and the digester become quite difficult to deal it. So therefore, for a small scale, that is possible. For large scale, certainly, we can't ship too far distance because of the cost involved. Yeah. But tipping fee is very, very important part of this whole system.
All right, bro. So because we only have more or less around 2 minutes, so this is maybe our last questions, yeah, bro. This come from Professor Afifi. I think this is more or less like a comment, because compared to the previous years, the early 50s, when you recycle bottle in the form of glass bottles, you get incentives from it. They'll pay you back. Yeah. But right now it says drinks come in Tetra Pak or reinforced paper, and that is almost impossible to recycle. I mean, like maybe in terms of the view of a recycling company as well of people, what are the pushing factor do you think that can propel this recycling thing?
Most of the recycling thing are essentially, many of the companies they do recycling because they get a tipping fee. For example, if I have to dispose something from my home, I have to pay a tipping fee. So many of those recycling company, we do it because we get, in the US, we have 5 cents per bottle. So they essentially getting, if you have a glass bottle with the marker, and then especially glass bottle and the plastic bottle, we get 5 cents per bottle or 5 or 10 cents, depending on the state. So you get this value. So people recycle because of that particular, the value they get. So that's one area. For the paper and other thing, it's essentially, I don't think there's anything you get. It's essentially you are doing because you are conscious about environment, and nothing is getting. And then those who produce, they essentially, If you put a large quantity, you are recycling. You're not recycling. You're just dumping out. But if you want to dump it out, you have to pay a tipping fee. So there is a what we call here we call the refuse derived fuel. So in many cases, for example, you have like cardboard, you have all the building materials, anything that bulky item, you have to pay about $125 per metric ton to dispose of. So this essentially involves the tipping fee that we pay for us to dispose of, and they take this and then goes into the what we call the waste to energy facility. They burn it, and then they essentially produce electricity. So they are making money because of the tipping fee. They said half of the revenue come from tipping fee and half come from the electricity production side. So that is essentially a private company doing this kind of job. Yeah. I hope that addresses some of the comment. Otherwise, population essentially has to be more self-conscious on recycling thing. There is nothing silver bullet in my opinion.
Yeah, bro. Actually, this recycling is for me is a culture, right?
Yeah.
Yeah, people needs to do it themselves, not because of some incentives of something. Yeah.
Yeah. There's two other, you have a stick rule of, like carrot and a stick rule. Or sometimes you have a carrot means you are getting as an incentive. Stick rule means you're enforcing, you have penalty involved. If they saw you dumping your paper waste into food waste, then you are penalized. So there is one possibility, like China is doing currently, is penalizing in Shanghai many area. If you are dumping your chemical waste into the food waste, then you are being charged, you are being fined. So that is one way. So carrot and stick purpose, approach is one way. You are essentially providing them some kind of penalty if you're not disposing properly.
Okay, bro. We would love to have a longer discussion with you. It's just that time is not on our side. So yeah. I'm sure you're okay with if people are gonna continue discussion. Maybe they send you an email. You don't ask you personally.
Sounds good. Not a problem.
Yeah, bro. Because I think we have exceeded around 3 minutes of the allocated time. So maybe if I can invite back our distinguished Dean, Professor Rafiq, to make some concluding statement.
Thank you, Zainul, for sharing and moderating the session. And I must say, Prof. Samir, thank you so very much to you for a very interesting presentation. Not just interesting, it is actually a very important topic. So thank you so much for sharing with us lots and lots of interesting stuff from you. And thank you as well for accepting our invitation in the first place to speak at our distinguished lecture series. And to all of our viewers worldwide, thank you so much for watching. Do stay tuned because we have many more lectures for you. So until then, bye-bye for now. Bye-bye.
Bye-bye. Thank you. Stay safe. Take care. Thank you, Daniel. Thank you, Rafiq. Yeah.